Hello all, welcome to the video lecture. I am Ramesh Lama. Today we will be discussing about image filtering. The name filter is borrowed from the frequency domain, where filtering refers to passing or rejecting certain frequency components. And there are different types of filters such as low pass filter, high pass filter and band pass filter. The filter that passes low frequencies is called low pass filter, and the filter that passes only the high frequency components is known as the high pass filter, and the filter that passes the frequencies of certain range is known as band pass filter. And here we will be discussing in more detail about low pass filter and high pass filter. And while talking about the filtering in image processing, it is usually referred as a smoothing filter. And if we try to relate the low pass filter and smoothing operation in image, the net effect of low pass filter is to blur or smooth an image. So we can accomplish a similar smoothing directly on image itself by using special filter, which is also known as mask, kernel and windows. So here we will refer to our filter as a special filter. So image filtering is really important in computer vision and image processing and some other applications. It is usually used to enhance images, and where some denoising, smoothing operations are performed, and we also increase the contrast to enhance the images. And it's also used for extracting information from images, and where we extract texture, edges and distinctive points from the images. And it's also used for detecting patterns for the template matching. So talking about the mechanics of spatial filtering, it consists of neighborhood or a small rectangular region, which is also known as patch. Nowadays it's also known as patch, and it also consists of some predefined operation that's performed on the image pixel encompassed by the neighborhood. And it also consists of filter mask with the filter coefficient, or we call it kernel. And after the filtering operation, it creates a new pixel with the coordinate which is equal to the coordinates of central of the neighborhood, and whose value is the result of filtering operation. And if we perform if the operation performed on the image pixel is linear, then the filter is called the linear filter. Otherwise the filter is non-linear. And we can here the figure shows mechanics of spatial filtering using a 3x3 neighborhood. Here we can see here the point xy. At each point xy, the response of filter at the point, like at this point xy, we can see here point xy, the response of filter at this point is sum of product of filter coefficients. Here we have filter coefficients w, and here this w, here this w, and it is the sum of product of filter coefficient and corresponding neighborhood pixels in the area spanned by the filter mask. And we can see here the area is spanned from fx minus 1 y minus 1 to fx plus 1 y plus 1, and the filter coefficients is spanned from w minus 1 to w minus 1 minus 1 to w1 w1. Here what happens is, like, we observe that the center coefficient of the filter ww, here the center coefficient of filter is W00, and it aligns with the pixels at the location XY and move the filter marks over the image and compute the sum of product at each location. We can see here the filter mask WW is aligned over FXY, and what we do is we move the filter marks over the FXY and find the corresponding sum of product. Like W minus 1 is multiplied with Fx minus 1 y minus 1, W minus 1 0 is multiplied with Fx minus 1 and y, and finally W11 is multiplied with Fx plus 1 y y plus 1. We can see here this Fx plus 1 is multiplied with W11, and Fx minus 1 y minus 1 is multiplied with W minus 1 minus 1, and similarly in this way all the pixels from neighborhood is multiplied with the filter coefficients and get the sum of product. Here gxy is the response of the filter. So in this way we get the filter response, or we get the filtered pixel, and this means that our focus is on following discussion is on the filters of odd sizes. Here we have like for the marks of size m by n, we assume that m is equal to twice a plus 1 and n is equal to twice b plus 1, where a and b are the positive integers. We can see here, and what we do is our focus is on the filter of odd sizes with the and the smallest size is 3 by 3. In this case what we have is 3 by 3 size, and in general the linear spatial filter of image of size m by n with the filter of size m by n is given by the expression. We can see here xy gxy is obtained by sum of product of wst and fx plus s y plus t. Here s and t ranges from minus a to a, and s ranges from minus a to a, and t ranges from minus b to b. This a and b will define the size of neighborhood, and as I mentioned before, the size of the filter is of odd size, and with the smallest size of 3 by 3. And now we'll talk about spatial correlation and convolution. There are two closely related concepts when performing linear spatial filtering, and these are correlation and convolution. Correlation is the process of moving a filter marks over the image and computing the sum of product at each location, exactly discussed in the previous section. We have just discussed in previous section, and we can express it in terms of product, sum of product, wst and fx plus s y plus t, and the s ranges from minus a to a, and t ranges from minus b to b, and here s and b, a and b will define the size of it will define the size of neighborhood, or this a and b is dependent of m and n, and m and n will define the this small m and n will define the size of neighborhood or size of window, or we call it nowadays it's also known as patch. And let's see the example. Here we have f image and w kernel or mask, and it is we have taken the neighborhood of 3 by 3, and our center pixel is f5, and we get the mask, and it also has center pixel of w5, and we perform the spatial correlation. What we get is the sum of product. Here the f1 is multiplied with w1, f2 is multiplied with w2, f3 is multiplied with w3, and so on, and finally we take the sum of product of we take the sum of product, which gives us the spatial correlation or the spatial correlation at the pixel f5. And we can see here example, like we have original we have image with the center pixel at 1, and we have filter marks, and what we do is we basically we pad zeros on the before we perform any filtering operation, and we move this the marks over the this we move the marks over this image and perform the sum of product, and finally we get the fully correlation result. Here what we get is at figure D we get the complete result after the correlation is performed, and finally we can see the cropped result. Here it starts with like 9. The final result is 987654321, and in this way we perform the spatial correlation. And convolution, while talking about convolution, it's also same as correlation. However, what we do here is we flip the filter in both dimension, from bottom to top and right to left, and then we apply the correlation. And for the convolution with the filter masks wxy and fxy, we get the following expression. The following of expression gives the convolution operation. Here fx minus s and y minus t will flip the kernel. We'll see here, like we have the image f and w kernel, and we have got the kernel w. First what we do is we flip it x flip, or we flip it in x direction. Then what we get is w1 w2 w3 is flipped to w3 w2 w1, and w4 is w4 and w6 are flipped, and w7 and w9 are flipped. Again what we do is we flip it in y direction, and we get the final flipped convolution kernel, and what we do is we multiply, we get the sum of product, and finally we get the result. Here what happens is f1 is multiplied with w9, f2 is multiplied with w8, and f9 is multiplied with w1, and finally we get the result after the sum of product. So we can see here the result, like if we see the result of convolution, like we have got the w, and we have got w which is rotated w or flipped w, and after we perform the convolution operation we get the result, and which is just the flipped version of the correlation. We can see here it is in the result here it's 1 2 3 4 5 6 and 7 9. However, in correlation it was like 9 8 7 6 5 4 and 3 2 1. We can see here, let's go back. Sorry. Yeah, here the result of correlation here, like in this case the result is just the flipped version of correlation. We can say it as a, like the result of correlation is flipped version of convolution, or convolution is just the flipped version of correlation. So the spatial filtering algorithms are based on correlation, and thus implement the equation of correlation. To use algorithm for correlation, we input w into it, and for convolution we input w and rotate it by 180 degree, and either of the equation of correlation or equation of convolution can be made to perform the function of other rotating by the filter kernel. what we have to do is just rotate the filter kernel. How about that the order of function in functions input to the correlation algorithm does not make difference, because correlation is neither commutative nor associative. Actually, if we look at the difference, if we look at the properties of convolution and the correlation, the convolution is commutative as well as associative. However, correlation is neither commutative nor associative, and both of them have common property, which is distributive. We can see here both correlation and convolution are distributive. And another feature, very important term in the filtering, is the separability. And we can say that our 2D function is said to be separable if it can be written as a product of two 1D functions, g1x and g2x, that is gxy is we can express it in terms of product of two functions. And a special kernel, a special filter is a matrix, and we know we have a special filter kernel or max, which is a matrix. We can see here the example of first matrix here with 1 2 1 2 4 2 and 1 2 1. This is a filter kernel, and it can be said, we can say it as a separable kernel when it can be expressed as the outer product of two vectors. Or we can see this is here we can see like this kernel is expressed in terms of this outer product here 1 2 1 and 1 2 1, outer product of two vectors, and it is now it's expressed in terms of outer product, and it turns out that the product of column vector and row vector is same as the 2D convolution of the vector. It means like if I break this into the column vector and row vector and I perform the convolution operation, then the separately if I break it into two row vector and column vector and I perform the convolution operation separately, then the net result will be same in case of separable filter. We can see here, like if we perform the convolution operation on this matrix 2 3 3 3 5 5, and it will be same as in case of 2D convolution or by performing the convolution with the separable with the two column and row vector. So why is the separable useful in practice? Actually, separability means that 2D convolution can be reduced to two 1D convolutions, one among rows and one among columns. We have seen just before, and if we have a kernel W that can be decomposed into two simple kernels such as W1 W2, then it follows the form of commutative and associative properties as discussed earlier, as shown in this expression. And this equation says that convolving a separable kernel filter with the image is same as convolving W1 with F first and then convolving the result with the W2. We can express this, we can say this expression like this. And what happens is, like, the complexity of the filtering of an n by n image with an m by m kernel will get the order of complexity will be order of n square m square. However, if the kernel is separable, and it will be reduced to order of n square m. So the separable kernel is basically used for the reduction of complexity, or we get like the complexity is highly reduced while using the separable kernels. And now let's come back to the filtering and generating a special masks. Now we'll talk about how to generate the special masks. And generating a m by n special filter requires that we specify m by n mask coefficient, which are selected based on what the filter is supposed to do. Suppose like now we are focused on smoothing filter, so we are trying to generate a special filter that will smooth our image. So suppose that we want to replace a pixel in an image by average intensity of a 3 by 3 neighborhood. Then what we can do is, if I have zi is equal to the I ranges from 1 to 9, and this denotes the intensities of the image, then the average is just we sum it and divide by 9. And same as in the vector representation, what we can specify the max coefficient Wi as a 1 by 9, and then we can perform the filter operations, and which is just same as the averaging of the intensities. So here we define the max by max coefficient with the ratio of 1 and 9, or the ratio of 1 and the filter size. So it is also, this type of filter is also known as a smoothing box filter, or average filter, or mean filter. It's very widely used smoothing filter. And what it does is, like, it replaces each pixel with the average of its neighborhood, and it achieves smoothing effect, and which removes the sharp features. Here it is, we can see the filter coefficients here in this figure, and here is the example of box filter. We have an image from the Hubble Space Telescope, and image processed by a 15 by filtering averaging marks. Here the size of the filter is 15 by filtering, and next is a thresholding. We'll discuss about the thresholding operation in subsequent classes, but for now let's just focus on the averaging mask, or just the smoothing filter. Here we get the smooth version of image by using the 15 by 15 averaging mask, and we can see the image is blurred as compared to the original image. We can see here the effects of smoothing as a function of filter size, and if we look at the size of the filter marks used and the net effect on that image, as the filter size increases, the effect of blurring is increased. We can see here the original image of 500 by 500 pixels, and B to F refers to the smoothing with square averaging filter marks of size m is equal to 3, like 3 by 3, 5 by 5, 9 by 9, and 15 by 15. And we can see here the first image is like the original is smooth with 3 by 3, and second with 5 by 5, and third by 9 by 9. And as the size of filter kernel increases, the smoothing effect or image looks more blurred, or the smoothing or the blurring effect gets increased with the increase of size of filter. Now we'll discuss about the smoothing spatial filter, even though the previous one also was the smoothing spatial filter. But what we observe that is the output of a smoothing linear filter is simply the average of pixels contained in the neighborhood of the filter mask, and by replacing the value of each pixel in the image with the average of average of intensity levels in the neighborhood, a smoothing linear filter will reduce sharp transition in intensities. However, the edges are often characterized by the sharp intensity transitions, so smoothing filters may have undesirable side effect on edges. That means the edges of images may get blurred. Thus, we go for the weight average. In this case, what we do is we give more importance or weight to the some pixels at the expense of other. Like we can see here two filter marks. One is the box filter or average filter, mean filter, and another one is the weight average. The difference between the two filter is like in case of box filter, there is no more importance is given to any specific pixel, but in case of weighted average, the more priority or more importance is given to the pixels in nearby the origin or nearby the center pixel, or more importance is given to the center pixels and the pixels or the from the far from neighbor center pixels are given less importance. And one of the example of this type of filter is Gaussian filter, and it's also used to blur the images and remove the noise and detail. Here we can see here it's also spatially weighted average, and in one dimension the Gaussian function is written as, like we can write here in terms of here it is we can see here it's written in terms of u square. Here u gives the pixel distance, and another important term here is the sigma, where sigma is the standard deviation of the distribution. And here what we assume is the distribution has a mean of 0. So what we saw here is if we take this as a center pixel, then the more importance is given to the center pixel, and the size of the filter is also defined by this sigma, or its distance from origin. And as this sigma increases, the size of filter will increase, which we will see in the subsequent discussion. We can see here the standard deviation of Gaussian function plays an important role in its behavior. And if we look at the figure here, the values located between plus minus sigma accounts for 68 for the set, while two standard deviations from the mean, blue and brown, account for 95%, and three standard deviations, blue, brown and green, account for 99.7 and account for 99.7%. And this is very important when we design Gaussian kernel of the fixed length. And when we are working with the images, we need to use the two-dimensional Gaussian function, and this is simply the product of two 1D Gaussian functions, one for each direction. Here a graphical representation of 2D Gaussian function with the mean at 0 0, and sigma is equal to 1 is shown in the right. We can see here this is the Gaussian function, and this is 2D Gaussian function, and it's approximated with the sigma is equal to 1, like it's sigma is equal to 1, and mean is 0 0. And the Gaussian filter works by using the 2D distribution as a point spreading function, and this is achieved by convolving a 2D Gaussian distribution function with an image. Like we get the filtering of image by Gaussian filter is achieved by convolving the 2D Gaussian distribution function with an image. So what we do is we need to produce discrete approximation to the Gaussian function, and this theoretically requires an infinitely large convolution kernel, as Gaussian distribution is non-zero everywhere. Fortunately, the distribution has approached very close to 0 at the 3 standard deviation from the mean, and 99% of distribution falls within the 3 standard deviation, as we discussed in previous section. And this means that we can normally limit the kernel size to contain only values within the 3 standard deviation of the mean. And the Gaussian kernel coefficients are sampled from the 2D Gaussian function, where sigma is the standard deviation, as we discussed before, and we can approximate our Gaussian function. And the distribution is assumed to have mean of 0, and we need to discretize the continuous Gaussian function to store it as a discrete pixel here, and here an integer of integer valued 5x5 convolution kernel approximating Gaussian with a sigma of 1 is shown in the right. This is the Gaussian convolution kernel with the sigma is equal to 1, and the Gaussian filter is a non-uniform low-pass filter. The kernel coefficients diminish with the increasing distance from the kernel center, as we have seen, and center pixel have a higher weighting than those on the periphery, and the larger value of sigma produces the wider peak, and that will ultimately create the greater blurring effect. And kernel size must increase with the increasing sigma to maintain the Gaussian nature of the filter, and Gaussian kernel coefficient depend on the value of sigma, which we discussed before, and at the edge of the mask coefficient must be close to 0, and the kernel is rotationally symmetric with no directional bias, so it is symmetric. So what we can do is, like, even if we perform the convolution or even if we perform the correlation, the net effect is same. So Gaussian kernel is separable, and which allows us for the fast computation. We have already discussed about what is separable Gaussian, what is separable kernel, and thus if we perform so the Gaussian function, so the Gaussian filter is which will allow us the in case of Gaussian filter we can have a fast computation, and Gaussian filter might not preserve the image brightness. And as we have discussed, what the parameter here matters, obviously the variance of Gaussian or standard deviation Gaussian, which determines the extent of smoothing. We can see here the shape of the bell, or shape of the, or the nature of the kernel, with the sigma is equal to 2 and with sigma is equal to 5. Obviously the sigma is equal to 5 will create the greater blurring effect, and we can see here sigma is equal to 3 controls the amount of smoothing, the sigma controls this amount of smoothing. Here this is the 15 by 15 Gaussian mask, and let's see with the small sigma and with the larger sigma, and we can see with the small sigma it creates a limited smoothing, while with the larger sigma it creates the strong smoothing. And if we compare it with the box filter or average swing filter, we can see that the it preserves the edges as compared to the box filter. However, we cannot guarantee completely that it will preserve the edge, but as compared to the box filter, the edge is marginally preserved in case of Gaussian filter, and it is all because of the nature that the center pixel is given more priority or given more importance than the other pixels, or we can say it as a net effect of especially it is the because of the weighted average, especially weighted average. And we can see here severability of Gaussian filter. The 2D Gaussian function can be expressed as a product of two functions, one function in x and other function in y. In this case, two functions are identical, 1D Gaussian function. So that's why, like we can see here, the Gaussian function is expressed in terms of two functions. So we can perform in the separable. We can perform these two functions in row, like we can perform it in terms of separable separately, we can perform the filter separately. And another type of filter is the order statistic filter. It's a nonlinear spatial filter, and whose response is based on the ordering or ranking the pixel content the region encompassed by the filter. And median filter is one of the example of order statistic filter, and it replaces the value of pixel by median of the gray levels in the neighborhood of that pixel, and it's also used for noise reduction. We can see here we have got the pixel values 3x3 window or 3x3 neighborhood, and we have got center pixel value 90. And in case of mean or average filter, what we do is we take the average of this value, this window. However, here what we do is we sort and get the median value, and the 90 is replaced by this 27. And what happens here is the advantage of using this median filter over the Gaussian filter or the median filter is it's robust to outliers. We can see here, like the among the if we look at the nature of these pixels, the 90 can be taken as outlier because it's the value of this is completely different from the other pixel values. So once we get the median, then we can see here this we can see here the response of we can see input and response of median filter. Like the outlier is shaped, has brought to the shape with the median filter. However, if we use the mean filter, that outlier changes, that outlier may affect the values of other pixels as well. However, in case of median filter, there is no effect of this outlier on the other pixel intensities. So if we look at the result, like the salt and pepper noise in image, and if we filter it with the median filter, we can get the better result with the in case of salt and pepper. Like we can say the salt and pepper as outliers in the image among the other pixel intensities. So if you compare the result of median filter with the mean filter, we can see that the quality of image is completely different as compared to the mean filter. Or we can see here X-ray image circuit board computed by salt and pepper. Here the salt and pepper noise, the image is corrupted with the salt and pepper noise, and we perform the mean filter. We perform the smoothing using the average filter, and also using the median filter, and we can see that the result of median filter is really better than the mean filter, like which is clearly visible here. That means it's highly robust to the outliers of the outliers in the image or in the distribution of the pixels.